we've had a look at the introductory ideas of work, energy and power. We're now going to look specifically at those three types that we mentioned in the previous video. First one here you can see is about kinetic energy, and just a reminder that kinetic energy, you can consider it to be the energy of motion, and specifically the energy of motion of a mass. Now, in order to identify the equation that's involved here, we're just going to go straight to a simple example. We're going to start off with an object of some description sitting on a flat surface that has a mass m, and I'll mention here that this surface is frictionless. So we're just going to simplify it. We're not going to worry about the effect of friction. Obviously, in the real world sense, then that does actually play a part, but just makes this analysis a little bit, or this description, a little bit clearer, a little bit easier to deal with. That mass is going to be accelerated by a force, and the initial velocity of this mass, again to simplify the explanation, will be it'll initially be stationary. Now, at some later point in time, that mass is going to have moved to a new position, and at that point it's going to have a velocity v. It's going to take a certain time t to get there, and it's also going to have moved through a distance. So if we use sort of the middle of the object, it's going to have moved through a distance s. In this case, we're going to assume that the force is constant, and if we are assuming that the force is constant, that basically means that we've got an unbalanced force. So we're dealing with Newton's second law, and as we know, if an unbalanced force is applied to an object, that means that the force is going to be equal to the mass of the object multiplied by the acceleration. But we also know that acceleration can be defined as, or can be explained as, the change in velocity. So that's the final velocity minus the initial velocity over time. So we can write that expression for acceleration instead. You'll see here though that we've got a term u, and we know that u is equal to 0. So in this case that simplifies down to be mv on t. We'll leave that one there for the time being. We'll come back to it in a second. If we look then at the distance, and hopefully you can see where this is going, we've dealt with the force, now we're looking at the distance. The distance at time t is given by the Suvat equation. So s is equal to ut plus half at squared. Again though, u is equal to 0, so that term will disappear, and we can again make that substitution for the acceleration of v minus u on t. So there's our acceleration multiplied by t squared. Again, the initial velocity is 0, so that term will disappear, and we've now got t squared divided by t, so this expression simplifies to become half vt. So there's our expression for force and an expression now for distance. The work done in accelerating the object up to the speed v, or in other words the work done by the time t, that work is going to be equal to force times distance, and we've already seen that the force can be expressed as mv on t, and the distance can be expressed as half vt. Now again you can see here we've got a t and a divide by t, so the t terms are actually going to disappear. We've got a constant of half, we have the mass m, we've got v multiplied by v, so we have v squared. So there's the work that's done in causing the object to move from its initial position, its initial velocity of 0, up to a final velocity of v. And coming back to that idea again that work done on an object means that it gains energy. So in this case the work done is in the form of kinetic energy. So we're doing work on it and the object is gaining energy in the form of kinetic energy here. we then have that expression for the work being done. We can instead express that as kinetic energy, and we use the symbol E with the subscript K, so energy in the form of kinetic energy. So kinetic energy is given by the equation half mv squared. That's a fairly important one in terms of looking at our energy equations. Note that that's moving an object from a velocity of 0 up to a velocity v. So once it gets to that speed v, if we remove the force, then the amount of work that we've done will be equal to the kinetic energy that the object now has. There's one last note to make here, and that's about if the initial speed wasn't 0. If you think about it, if we start off with an initial condition where we're looking at an initial velocity half mu squared, and then it accelerates to, let's call that EKI for initial, and EKF for final, that would then be half mv squared. So once it accelerates from u to v, we can then actually talk about the change in the kinetic energy, and that will simply be the difference of those two, so half mv squared minus half mu squared, and so we could then express that as half m outside of v squared minus u squared. So one last little thing looking just at the change in energy that can occur there. Moving on now, there's another type of energy that we're going to have a look at in this video, and that's gravitational potential energy. And this, the derivation of this equation is much simpler. Just recall that the gravitational potential energy is energy stored due to an object's position in a gravitational field. And when we talk about an object, we're really talking about something with mass. So it's more so it's the mass that's important here. And we'll again look at a simple example. So starting off with, say, an object that's on the ground that has mass, and we're going to lift that object into the air, and again we're going to use a constant force, and now the distance that we're looking at here is going to be the height h. We're just going to jump straight to calculating the work done lifting the box. To that height h. So again, we know that work is equal to force times distance. Note here that the force is in the direction of the distance that we'll be moving, and because we're moving at a constant speed in this case, the force that will be applied here is just equal to the weight of the box itself. So that force that we can express there is, instead of F, we can write that it's equivalent to the mass times acceleration due to gravity. So that will be the force F, and the distance that we're dealing with is the height h. So the energy here, or the energy that's gained by the box, the energy gained, in this case it's gravitational potential energy. I'm just going to abbreviate that to GPE. And so we can write that equation as being EP, so P for potential is equal to mgh. And again, another important equation there to deal with energy. So a fairly easy one to deal with there. One last bit about gravitational potential energy, though. More often than not, we're not just going to lift things from the ground. So it might instead be that we've got an object, say, sitting on a table, and then we're going to lift it to some new height at a greater position above that table. So we might actually say that we've got the height of the table that we need to consider, and then the new height that the object's being moved to. So more generally, what we're going to see is that we'll be talking about the change in potential energy, and that's going to be equal to the mass of the object multiplied by the acceleration due to gravity by the change in the height. So that's I think, in fact, that's the equation that's in the data booklet. So the change in potential energy being equal to mg times delta H. Now, making this a long video, there's one last collection of ideas that we need to deal with here, and that's the conversion of or conversions between GPE and KE. And again, going straight to an example, in this case I'll be a little bit more specific. We're talking about a ball rolling down an incline, or rolling down a slope. And again, to simplify the matter, we're going to imagine that friction here is negligible. So we start off with an object or a ball up here, and it's going to be raised some height h above the ground, and at some later point in time it's going to have rolled to the bottom here, and it's going to be moving with some speed, and that ball has a mass of m. So we can identify that up the top. Initially, because the ball is being held stationary at this point, should make that note as well. When the ball is held at that position, the initial form of energy is potential energy. So we can write that EP is equal to mgh in that case. And then at the bottom, we're going to have all of that energy is going to have been converted into kinetic energy, because there's the height here is now 0. The ball has now started to move, and so its velocity, its speed has increased. So at the bottom we can say that the energy is now kinetic, so half mv squared. So we're looking there at just a transformation of energy from GPE to KE, and due to the law of conservation of energy, if we consider friction and spell that right, friction and air resistance to be negligible, so we're not going to consider those factors. We'll imagine that they're so small here that they don't play a significant factor. What we find is that the total energy of the system will always be the same. So initially we've got GPE, and at the end we've got kinetic energy, KE. So we can say that the kinetic energy at the end is going to be equal to the potential energy at the beginning, considering that all of that potential has been converted to kinetic. If we then substitute into those equations the expressions for each of those quantities, so instead of EK we're writing half mv squared, instead of EP we're going to write mgh. Notice there that mass is constant on both sides, so the mass here doesn't actually play a part, so we're left with half v squared is equal to gh. If we do a bit of algebra here, we end up with v squared is equal to 2gh. We can actually calculate the speed at the bottom will be equal to the square root of 2gh. So just by knowing the height with which the ball has been raised, or from the height that it's been released, we can calculate the speed with which the ball will roll down the bottom. Incidentally, we could do that for any intermediate height as well. So if we wanted to figure out how far or how fast the ball was rolling by this stage, all we'd need to do is figure out what the change in height is between its initial position and its new position there. So we'll have a little bit more of a look at some of these sorts of ideas in class in terms of energy conversions. There are a few other scenarios that are useful ones to identify and to have a look at, the way that the energy is converted between GPE and KE.